Hello everyone, I hope everything is working well. This is Luboš Pirkl from CFD Support, and I'd like to welcome you to the webinar where we are about to show you a comprehensive simulation workflow of Francis Turbine in TCAE, which is a simulation environment with substantial value at very reasonable costs. I hope everything is working well. We are running live, so in case of any technical problems, feel free to contact us and we will gladly answer all your questions and comments. There will be a webinar recording available, so you can be sure that you can see everything again if you like. And yeah, as usual, we have a lot of stuff to show, so make yourself comfortable. Please do follow carefully and think about what it is that you need to improve your simulations, and feel free to tell us. At the end of the webinar, there will be a Q&A session dedicated to your questions and our answers, so feel free to ask your questions. Ask your questions anytime during the webinar. You can find a question form in the menu, somewhere in the menu when go to webinar. So feel free to ask your questions or send us an email later. We'll be happy to help, and I think this is going to be it from this introduction, and I think we can get to the action. So please let me quickly introduce us. So this will be, as usual, this will be me. My name is Luboš Pirkl, and my current job here is telling the world about CFD support. Right next door is sitting my colleague Radek Máca, who is our head engineer and senior developer, and he came today for the first time on his new shiny motorcycle to show us. So let's check him out. Knock knock, Radek, how are you and how is your new motorcycle?
Hello, Luboš, and hello everyone who is watching. Yeah, it's incredibly fast. So
okay,
maybe I will sell it tomorrow because it's
okay,
too fast.
to save your life.
Yeah.
Okay. Anyway,
All right.
in the meantime, we'll do this webinar. So I'll continue with the agenda. So as usual, in the first part, I will give a general introduction to show what has been done and what's on the table. In the second part, Radek will give a live presentation of TCAE. It will be step-by-step example of how to set up and run and evaluate and to have done a Francis turbine. And finally, in the last part, there will be a Q&A session dedicated to your questions and our answers. So feel free to ask your questions anytime during the webinar. Some questions will be answered right away during the webinar. The rest will be answered later via email, but you can be sure that all the relevant questions will be answered, and yeah, it's very important. Your feedback is very important for us, so feel free to ask and we'll be happy to answer. So very quickly, about our company. The company is called CFD Support. It was founded in 2009. It's located in Prague, Czech Republic, and at CFD Support we deal with engineering simulations. We primarily focus on development of CAE software, which has very high added value for its users. It's primarily CFD and FEA software with its combination with FSI, etc. So TCAE is definitely a high-end software, and our clients are CAE professionals who know well what they want. We are obsessed with the accuracy. Accuracy is of our highest priority, and besides accuracy, we are focused on automation, repeatability, and application-tailored solutions. On the other hand, we don't believe in general purpose codes. We don't believe that any particular software can accurately simulate everything or that anyone can simulate everything. We do believe that any successful project is a result of focus, skills, experience, patience, and dedication. We believe in open source. Especially we believe in a combination of open source and professional support. So far we have invested more than 30 many years of focused team development on top of open source to deliver professional simulation tools like this, and that's why we are being picked, and we'll be happy to show you in today's webinar. We have very strong team of developers, and in TCAE, we have successfully merged the benefits of open source with the benefits of commercial codes. So due to the open source nature of the code, the code is unlimited, it's extremely flexible, and due to the commercial code nature, TCAE has a graphical interface, it has professional technical support, it's robust, it's accurate, it's automated, it's well tested, and it's ready for use in the industry. And this is how the graphical interface looks like. The user can do here everything from the simulation setup and the simulation run to the detailed post-processing of the results. And besides this graphical interface, there is a batch mode available, of course, and TCAE can be run within another software or inside a comprehensive simulation chain. So TCAE consists of software modules that can be combined according to the project needs, and you can view them as an independent standalone tools, which make together a complex workflow, but you can use just one of them or all of them or any combination. And yeah, TCAE has a modular character. That means that the user can choose between TCAE modules if needed and combine them with many other software pieces available in the market. So the total number of combination is almost infinite. TCAE has strong integration ability. It has been from the beginning developed in a way to fit any existing workflow, no matter if it is combined with commercial codes or in-house codes, or if it is combined with another open source code. TCAE is very flexible because, as you know, in a typical enterprise, the engineers, they usually have some existing workflow already, and TCAE is capable to fit into it. And no matter what design tool is used, no matter what simulation tool is used, TCAE is still here to fit in any workflow and to do its job and deliver the results for the user's judgment. TCAE is very flexible. It's ready for very complex workflows, and we believe it's modern code. Yeah. TCAE is unlimited. It means there are no limitations on number of its users, and there are no limitations on the number of the jobs and cores it's being used with. No matter how many hardware installations are used, so that it's very useful. It can scale all the resources to the fullest, and it's very accurate. It's our biggest priority to be accurate, to be focused. It's accurate because it's focused on mainly turbo machinery simulations and external aerodynamics. These are two fields we are focused on in a big way, I would say. It's definitely not a general purpose code, and we believe it's the experience and dedication which makes it accurate. It's perfectly automated, so it can be used as a black box or as a fully or highly sophisticated code. We believe we have good technical support. It's created in parallel for Windows and for Linux, and of course native compilations, natively compiled, and it can be used remotely or in batch mode. The automated meshing system is included, is available, and of course the external meshes can be loaded. It's the user's decision. and there is very advanced post-processing, especially for turbo machinery. We have very good post-processing, a lot of features installed and developed, and we are happy to show you. Okay, I'll continue what needs to be said. Yeah, we have continual development. So as you know, the software is never finished. It's always in the development process. So there are a lot of versions we have released, and there are a lot of versions we will release in the future. It's users driven. I mean, the development is based on the users' requirements, which we gather together and pick the most important capabilities to implement them for the next releases. We have a special system for the development. Recently we have released the new version, which was in February, so it's not that new, but in February we released 21.02 version. We are already in the full process of developing the next new version, which will be released in September. There will be a lot of interesting new capabilities. There will be again better graphical interface. There will be, for example, support for real gases. There will be extended support for heat transfer. There will be a much better CGNS library, export and import. And there will be definitely a big thing, which will be new module, which is designed for the optimization. I'm sure there will be a lot of information released later. And even more in the future, we are definitely focusing on acoustics, which is again our next or currently running a big development project, so you can look forward to it. TCAE has always been best for turbo machinery applications like pumps, fans, hydro turbines, like as you can see in today's webinar, and compressors and turbochargers and all the rotating stuff, and also in the combination of external aerodynamics and rotating machinery like wind turbines, for example, or car bodies and or the aircraft, or various internal flows like valves, hydraulic valves, exhaust manifolds, intake manifolds, and ship propellers, or even ship hulls with propellers, or drones, or for example, the building wind loads and human comfort and heat transfer. There are a lot of benchmarks we've shown in the past to really prove TCAE is very accurate if it is used in a proper way. But today's webinar is about the Francis turbine, and I'm sure my colleague Radek is ready for his contribution. So I'm right now going to hand over the presentation over to him. So Radek, do you think you could take over?
Yes. Just let me know if you can see my screen.
Okay. So when we see it, I will tell you.
So
we can see it now. So I think you can start your part.
Okay. So thank you, Luboš, for handling the presentation. So today I will show you how to set up the Francis water hydro or Francis hydro turbine case. The case is available on our web pages. So if you go to the TCAE section, you will find this Francis turbine case. So you can download it and you can try it on your own. So today I will basically show you how to prepare similar case for running CFD and FEA analysis from the existing STLs. All right, so I will directly jump into the case setup. So at the beginning, we will have just the STLs. So the STLs has to be prepared and generated in a proper way. I think in several past past webinars, we have mentioned, let's say, the properties and the topology of the component thinking, so I will be not repeating this. And we will directly take these STLs and we will use them for the meshing, and then we will set CFD and FEA simulation. So just to present the STLs we will be working with, I will just load them into the ParaView, and I will show you the topology of the current Francis turbine design. So yeah, this is the simulation domain. The simulation domain has to be split into the meaningful part. We call them components. Usually we split the components into the stator and rotor parts. So at least here we have 3 components. One component which includes the spiral and the guide vanes. Then there is interface including the rotor part, and then we have a part which builds the draft tube. Each component needs to be waterproof or watertight, so basically it's a closed domain, and the neighboring STLs are fitted perfectly for 2 neighboring components. If we would like to do also the FEA analysis, we need to have also a STL for the solid, which defines the impeller solid itself. So we need to have one STL for the whole impeller, which will be then meshed in the T-mesh module, and then for this mesh, an FEA analysis can be set. So basically, we will be working with this. In general, the splitting of the STLs has to be done in the way that we can then exclusively define the boundaries and the boundary conditions. So we need to have inlets, outlets, rotating, non-rotating parts. That's basically all what the input STLs have to satisfy it. Okay, so let's jump into the TCAE. So I'm now working in Windows, but the similar approach can be done in Linux, on Linux machines. So I will just click the TCAE 21.02. Yeah, we are using the latest version v2, and let's start. So if we open the TCAE, we have let's say the plain setup, and we will start with a really step by step as a wizard. So starting from T-mesh over TCFD setup and TFEA setup. So at the moment, I will switch off the TCFD and TFEA module, and I will go for the T-mesh module. So in general, first I will be setting up the CFD mesh, and afterwards I will also add the FEA mesh, and then I will enable again the modules for CFD and FEA analysis. So let's start. So here what we need to set correctly is the scale factor, which basically defines the input units of the STLs. So our STLs are exported in meters, but some CADs, for example, can export in millimeters. So then if the original units are millimeters, then you need to set 1 millimeter is the original dimension for all the STLs. So in CFD mesh, we will start setting up the mesh basically. First menu includes the rotation reference frames, which is basically the rotational transformation, which will be then used for also defining the rotation. But for example, for some segment cases, for axial machines, it is also used for defining the transformation between the periodicities. And so therefore we always, for the turbo machinery, we always need 2 frames, one static and one rotating. Usually both of them has the same axis rotation. So in our case, I think the the turbine is aligned with the Z direction. We can then check it when we will load the geometry, but I will set it up because I know my input geometry. And that's basically all. The rotation itself, the speed of the rotation is then set in the TCFD module. In the components, the main, let's say the main game happens. So here we load the input geometry and set the parameters of the mesh. So as I already mentioned, this case has 3 components. So spiral spiral with the guides, then the impeller itself, and the draft tube. So we will have 3 components. We can enable the turbomachinery case. So there is some specific parameters for turbomachinery cases, like types of the boundaries, including blades, hub, shroud types, and other useful turbomachinery features. So I will go step by step. So first component name. So it is a user-defined name. So let's say I will start with the spiral or guide. Will be the first component. Impeller will be the second component, and the third component will be the draft tube. Let's say the second parameter is the reference frame. Reference frame means if the component will be treated as a rotating. So the simple rule, if the component includes the rotating parts or the impeller, the whole impeller, then you should set it as a rotating component. So spiral is non-rotating, of course, impeller is rotating, and draft tube is non-rotating. Now for each component, we need to define the mesh input. So today we will work with the STLs, but you can also use an external mesh in a Fluent, OpenFOAM, or CGNS format. So if you have any meshing tool, you can generate the mesh in that tool and then import it here into the TCAE. But today we will work with the STLs. So I will locate the STLs for today's case. I think I placed it here before the webinar started. So here you have Francis Hydro Turbine from scratch, and here I have the directory with all the STLs. So I will click OK. Whenever I clicked OK button, all the STLs are loaded into this table. And now in the first step, I will start assigning or enabling the proper STLs part to define the spiral component. So here what we have for the spiral, then the spiral in my case includes also the guide vanes, the guide blades. So I will basically you enable the STLs by setting a proper type. There are several types somehow connecting to the turbine machinery from, let's say, hub, shroud, blade, particular parts of the blade. And so basically in the background, it's a standard rigid walls, but it is set in this way to be more, let's say, user-friendly, and this type or this name will be also copied in the later, let's say, in the mesh itself, in the boundaries. So it's, let's say, much user-friendly and clearer to distinguish between each part. If, for example, the input names has some random names or just numbers on, and so this name will be also, this type will also appear in the resulting name in the mesh of the given boundary. So let's start. So guide blade, we can, because it's blade, we can set the type blade. Hub, we can set as a hub. It's the same for the shroud. Now I would like to see what I have enabled. So I can click apply, and my setup will appear in this render view. So this is my already defined names, no names, defined parts. And basically we can continue. So this is just hub, shroud, and blades. Then I I think there is a part which is called spiral, which is the spiral itself. So I will set standard wall part. Okay, and I think there is a little part here which connects the cutwater part and creates the, let's say, one of the blades here, and it is a spiral dip. So I can set it also, for example, as a wall. And now, if you see it, it is already there. What I like also, if you this geometry is saved or visualized by this item within the TMesh module, so you can anytime hide it or unhide it again or visualize it. What I like, if you click this item and you click display, you can make it an opacity to see what is inside. The default, let's say, coloring is that all the boundaries owning by one component is colored with the same color. But if you, for example, switch to this VTK composite index, then each boundary is visualized in the different color. So it's also sometimes useful for setting each part. And what is also handy, if you apply a slice on the CFD geometry, so you can apply the slice and the properties, and you can set the properties in the properties part here in this menu. So I will make a slice just in the middle, and basically what you can see here now is a contour, and you can sometimes check if the contour is close, which will show you if all the parts are set in the proper way. So it is also good visualization for checking the current setup. In the display, you can, for example, set the line width to be more thick. And yeah, this is also a nice feature. You can change the coloring to the component coloring and so on. So you can combine any, let's say, paraview features with the TCAE objects. So what we can see that still, I think the inlet and outlets is missing. So let's go back and we will set the inlet. So inflow will be the inlet pressure. Okay, so this is in the inlet and the outlet is missing because it's interface. So it is named like the interface and the proper name is interface. This is the guide to rotor. Yeah, so this will be the interface. There are three types of interfaces: inlet interface, outlet interface. For interfaces where flow direction is known, and free stream interface where we don't know the direction of the flow. For example, if you simulate an open impeller like ship propeller, so you need to enclose it into the cylinder, for example, to define a proper rotational part. And on this cylinder, on this single interface, because you don't know where exactly the flow goes in and flow goes out, so then you can set it as a free stream interface. But for this case, this is the outlet interface because this part creates the outlet from the guide or from the spiral part. So if I enable it, so I can see that this contour is closed, and I know that I also define the inlet. So I think this part defining just or enabling proper patches, defining the patches is done for this component. And this we need to done for also for the component 2 and component 3. So probably I will go back for the, let's say, component coloring. So component colors. So now everything is red, and now I will be adding the second component, which is the impeller. So again, I will load the same STL directory, and now I will define the rotating part, the rotor part. So for example, let's start with the blade. So blade rotation, blade rot is the STL which includes information about the blade. So I will set it as a blade. If I click apply, yeah, you can see the blades. Maybe now is good moment to mention that it is clever to save the current setup of TCAE onto your disk, onto proper let's say project folder. So we can go, in my case, I will put it into the same folder as the source STLs were placed. So I will go for webinar, Francis Turbine from scratch, and here I will save, for example, webinar setup. Okay, so my current setup is now saved, so I'm also saved. If I lost something, I can anytime reload it, my current setup again. So let's go to the T-Mesh part again, back, and let's finish the component 2 setup or defining the boundaries. So what is the rest? So I think hub is defined as these 3 STLs. So I will enable them as a hub types. So setting the hub, apply. Okay, so this was the hub part. I think shroud rotation is shroud rot is the shroud part. When we focus more, yeah, so I think hub and shroud is defined. So I think only two parts are left. So the inlet into the rotor and outlet from the rotor. So here we have 2 interfaces, rotor to draft and rotor to guide. So this is the inlet interface, and rotor to draft is definitely the outlet interface. So let's see if the contour is closed and if we can see all the patches. So I think yes, everything is there. So I think we are safe, yeah, and everything is correctly defined. And the last component, so again, load the STL folder and define the draft tube. So here we have just the draft tube wall, I think. So it will define the draft tube, yeah, boundary. You can say nicely here, and then only the inlet and outlet. So here we have draft to rotor interface. So here it is an inlet interface, and the outflow is a physical outlet. So there is a simple type outlet to define the outlet. All right, so here we have, I hope, correctly defined boundaries based on our input STLs. And now we need to set the meshing parameters. So let me save the current setup. And now we need to set several parameters which defines the parameters of the mesh of the cell, the refinement, and so for the refinement, there are basically 2 main parameters. One is then, let's say, overall cell size for the whole mesh. So this is basically definition of the largest cell in the domain, and then local refinement for each boundary. So let's start with the component 1 to show how it works. So usually you need to find the proper sizing of your cell. So for this, let's say, training purposes, we can go for a rougher mesh. And basically, if you start with the new geometry, I always start with a rough mesh, let's say, which nicely mesh your topology, your geometry. And then if everything is okay, everything is fine enough to let's say to follow the input geometry, then you can start to refine the mesh, adding the layers and so, but only from the state when you are satisfied with the mesh, and then you can start, let's say, make the mesh finer. So usually we start with the let's say cube cell, so same size in all the direction, and I think a proper size mesh for this current setup or for this geometry is something like 12 centimeters. So if you would like to see how it looks, you can enable this show background mesh wireframe. You will see, let's say, the topology, the sizing of the initial mesh with respect to your component and to your geometry. Maybe I will just quickly say about this background mesh sizing and the refinement. I think it's on this slide. You can download it also, this presentation from our web. So first, this background mesh size defines the, let's say, the initial mesh from which the meshing itself starts. And the meshing is done in the way that all the cells which are splitted by the input geometry are defined or are refined based on the number which is called the level of refinement. So then these numbers next to the patches defines how many times the cell is splitted if the cell is intersected by the given STL. So basically first, yeah, we have the background mesh, and then we will set the local refinement for each blade, and then the refinement is done by the level of refinement. You can imagine in that how many times the cell is splitted in the similar cubes, in case of cubes, or in general in case of a general hexahedra. All right, so let's go back to our setup. So I will let's keep with this, and then we will define the parameters. Okay, so this will be our initial mesh. The internal point is very important, which defines which part of the mesh will be kept. So basically, as you can see, you have definitely two options. You can mesh your object from the outside or from the inside. So therefore, you need to set a point within the background mesh, which will define the part of the mesh to keep for the simulation or to keep for the finalization of the mesh. So definitely we need to put this point inside. Yeah, so you can enable the show internal point and place it manually into the spiral part. So this radius is just for the visualization. Yeah, so defines it is used just for the visualization. So we need to put this point inside the spiral. Okay. Now we are satisfied. And now it's time to set a local refinement. So let's say usually some more detailed part has to be refined more important part has to be refined more, and let's say less important part and smooth part, so some lower level of refinement is acceptable. So let's start with an initial guess. So because the blades are pretty detailed compared to our initial background mesh size, so I will set, let's say, the level 3 for blades. Let's say for hub, you can visualize each part if you double click it. So if I double click the hub, then the hub part is visualized. Yeah, so which is also a nice feature during this mesh setup. Then you can delete this let's say highlighting by this icon. So let's say I will keep homogeneous name, which means it will be refined always with the level 3. Inflow has no importance with respect to refinement. Interface guide rod, because it's close to the blades, let's say, and the interfaces, let's say, should be fine enough for a good interpolation between them. So I will also use the same refinement as for hub and shroud. The spiral is, I think, is the biggest part of this, and it's both, let's say the smooth but also detailed here in this cutwater area. So we can set, let's say, level 1 for this, for the, let's say, flat and not so detailed part, and level 3 for more detailed part. So this is done automatically based on the local curvature of the input geometry. And spiral dip, I think, is the part of the cutwater which somehow creates the, let's say, one of the blade. So I will set the same level 3.3. So usually, if you set the homogeneous, let's say, refinement, so the same levels everywhere, makes the best mesh, but sometimes it will require really a lot of cells. So sometimes you need to set the level of refinement in the different numbers for different boundary parts, of course. Okay, so let's see what we have set. So now we can try to mesh this part. So I will save it and I will click check setup, which is a good let's say button, which will show you if something is set correctly or not. And now we can see, let's say, one error message: all components of the background mesh size for component 2 must be greater than 0. Okay, this check always check for the whole components, and until now we have set only the first component. So we can see that, for example, component 2 has the background mesh size this 000, which is not allowed. So I will set for now the same sizing for the whole components, for all the components. So it is 12 millimeters, centimeters. Okay, apply, and now I will try it again. Save and check. Okay, all right, very clever button. I haven't connected the interfaces. Yeah, so now we need to go back, and what I haven't done yet is that, okay, we have defined 3 components, some interfaces, but we didn't define how these components are connected. For example, to see the topology of the mesh, there is a component map. So if I double click, I can see it here. So we have 3 components, some with inlet, some with physical outlet, but there is no connection yet defined. And this connection is done by clicking on the something interface type. And if you right click this outlet interface, then you have a menu using which you choose the neighboring interface and basically neighboring component. So this outlet from the guide or from the spiral part has to be connected to the impeller part, and this connecting interface is this rotor, not rotor to draft, but rotor to guide. So if we click it, now we can see, let's say, a proper connection, and the same I need to do for the second couple of components which are connected, which is the impeller and draft tube part. So this is this, and the rotor is connected, the outlet from the rotor is connected to the draft tube. All right, so this is the connection. Now let me save it, check setup, perfect. Now case setup is okay, and now we can run the meshing for the first component. Before I do that, I realized that I haven't set a proper, let's say, number of processors. So my computer has 10 processors, so I can use 10 processors for the meshing, which will also speed up the meshing process. So let me set this parameter. So again, to be sure, I will save it. Now I will, when we are simulating something or running, so we need to first define the directory name in which let's say my project or my simulation will be stored. So let's say, I don't know, webinar case, for example. So apply. First, I need to hit the right button because all the setup and all the, let's say, hierarchy of the case is written down. And then I can run the meshing of the first component of the spiral component. So let me click it. This is the output from the let's say from the processor, CAE processor, which is running behind, and it is telling you what it is doing at the moment. And you can also switch to the solver output itself. So if you are familiar with the SnappyX mesh, then you can see the log of the SnappyX mesh here. So the mesh is done. You can visualize it by this show button. So if I click it, then in the render view, this newly generated mesh will appear. This mesh is stored with this CFD mesh item, so I can get rid of the other items to just visualize the mesh. And if you click it, you can, for example, choose the surface with edges to see the topology and check if everything is okay. So if we zoom a little bit, so we can see there are several, let's say, errors and flaws. So for example, here we can see that here are some, let's say, cuts or distortion of the mesh. So I think this could be caused that our refinement on the walls is not enough, and also the cells are too high to fully, let's say, fill the gap between the guide blades and this outlet interface. And similarly, this cut water part needs also a higher level refinement. So now we can go back to the T-mesh and set a high level of refinement for these parts. So again, we can visualize, for example, this and check which parts needs to be refined more. So for example, now the spiral dip is highlighted, so definitely it will need high level of refinement. Similar with this part, which is included into the spiral part. So I set the maximum level of refinement to 4, and the guide blades definitely needs also high level of refinement. And to be sure, you can see that the topology is also nice on this outlet interface. So the outlet interface will definitely need high level of refinement too. So interface guide rod is this. So I will set level 4. Okay, now I need to go back to the TCAE manager item. Here I need to write the new parameters on the disk, and then I can click on the build mesh again and check if my second iteration will be better. And basically, this is, let's say, this is the procedure, the workflow for setting up the new geometry and new mesh. You always need several iterations to be satisfied with the mesh topology, because it always, there are, for the detailed or more complex geometries, you really need to play around and locally check and refine all the parts to nicely follow the input geometry. Otherwise, the result will be somehow broken with respect to the bad meshing. So in general, the mesh quality from the parameters, mesh parameters point of view, can be fine, but the mesh itself doesn't follow your original geometry, so then it will definitely affect the results. So this always needs a visual, let's say, visual inspection. Okay, so let me visualize the new mesh again. So I will get rid of the other parts, not CFD mesh. And if we zoom here, so we can see that there are no zigzag shapes, let's say no cuts. So I think for, let's say, for the roughest options, it is a good mesh. Definitely then when your simulation works, then you can start refinement everything and check if the results are moving somewhere to somehow provide some, let's say, mesh convergence study. But always start with the roughest possible mesh, because everything then goes fast, and afterwards when the results and everything looks okay, then you can refine the mesh more and run the simulation again. All right, so this was the first mesh, or first component. So let's do the same with the second component. So I will again visualize the whole geometry, whole topology. And now we are setting the impeller part. So what I like, for example, the impeller is the most important part, so it will deserve much finer mesh. So you can, for example, make the background mesh finer than for the other parts, which is not so, let's say, important or not so complex. So I can make the background mesh of a half of the size of the component one, and which still, I don't know, holds me the proportion between the component one and component two. So I can still keep the same sizing of, let's say, for the interfaces, because if this background mesh size 0.06 and the first one is 0.12. So for example, if my outlet interface is 4, then to keep the same refinement, because the interfaces uses some interpolation during the simulation, so it's clever to keep the same sizing of the cells on both sides of the neighboring components. So on the inlet interface, I can set level 3, and because of my combination of background mesh sizing and level of refinement, it will keep me the same sizing of the mesh on both sides. Yeah, so it's also, for example, clever setup. So let's set the parameters here. So blade, for example, is the most important part from the whole case, let's say. And if you can see, the blades are pretty thin. So we can, for example, set the minimum level of S2 and the maximum level S4 to better follow the trailing and leading edges. So for the hub, I will, let's say, set the same level 2 everywhere, and I think I can keep it also on shroud. And on the outlet interface, which is a nice disk, and I think there is enough gap between the lower part of the blades and the interface. So I think the level 2 will be, or should be, okay. And last thing to set at this point is to put the point into the impeller part. So let me find a proper place, so somewhere between the blades and inside the impeller. So I think this should be okay. So again, I will apply it, I will save it, I will write the case and run the impeller meshing. Okay, let's build it, and just to fill the time, I will start setting up the last component. Last component is just a draft tube with not much detailed part. There is, let's say, no detailed part, so I can keep the rougher background mesh size. The draft tube, let's say, I will refine to level 1 and maybe some edges to level 2. This could be okay. Interface, okay, on the impeller side there was level 2, but for the finer background mesh, so I will set level 3 to keep the same sizing of the mesh on both sides, and outflow doesn't need a refinement. And we can put the internal point into the draft tube. So just let me check. Okay, I am in. So let me save it. Okay, so impeller is still meshing. So maybe we should wait a little bit. Okay, meanwhile, I will fill it with the improvement of the draft tube mesh, and I will show you a new feature. So we can see that, for example, we have set pretty rough mesh in the whole draft tube, but for example, what will be clever to make some refinement in the wake area below the impeller to better, I don't know, follow all the recirculation. And so we can set it by this at the refinement regions. So you can use them. So you can use it allows to define a simple shape, like for example cylinders. So I've aligned with the axis of rotation, and I will set it somewhere below the impeller. And this will allow you that all the cells which are inside the cylinder and of course inside the component, the blue one, and the draft tube, will be refined to the given level. So I can set that all cells which are within the cylinder will be split twice. So then I will have finer mesh in this wake area. And for example, because I would like to save some cells, so I would like to, for example, refine other cells which are more below, just to the level 1, for example. So I can define another cylinder, but for example, I will put it more lower, and here I will set level 1. So then I will see that some gradual refinement from the impeller to the bottom. Okay, so save. All right. Yeah. Meanwhile, the impeller is finished, and I will run the draft tube simulation or draft tube mesh generation, and we can visualize the impeller mesh. So again, I will enable it here. So I will show the CFD mesh, and I will hide the CFD geometry, and I can get rid of the spiral part. And this is the mesh for the impeller. Okay, back here. So I think it's a good start. I think very good start for our training purposes. And anytime afterwards, you can refine it more to follow your needs or your goals of the simulation. And the draft tube, right? I can add the draft tube, which is already finished. And to see what is inside, I can make a slice, for example. So again, on the CFD mesh, I can enable a slice with the proper parameters of the cutting plane. So I think to cut it somewhere, yeah, this could be okay. And surface with edges. So now we can see the topology. Yeah, so we can see the gradual refinement of the mesh. So this is, let's say, what I need. So I think I am very satisfied with this, and I can finish the meshing by the merge button, which puts everything together and creates one mesh which is ready for the simulation. Okay, so this, let's say, of course we can visualize the whole mesh just to see how it looks, but we have already checked all the parts there. So I think that this is okay. All right, and now it's time to set a FEA mesh. So because we would like to perform both simulation, CFD and FEA, we need to use the CFD and FEA mesh. And when I go to the bottom, now we can see the new menu for setting the FEA mesh, and this situation much simpler. So we need just load the solid STL, which defines the solid. You can also use some NetGen or Abacus external meshes in a NetGen and Abacus format. sorry. And now basically we need to set just two parameters. Was it the maximum sizing of the tetrahedra and minimum sizing of the tetrahedron, or tetrahedra within the mesh for FEA analysis? So in this case, it is a tetrahedral mesh, and this mesh is generated by the NetGen engine. Okay, so let me speed up the settings. So I think based on the sizing of the impeller, let's say we can set the largest tetrahedra or largest tetrahedron to 5 millimeters, centimeters, and the smallest one, because the blades are pretty thin, we can set it to 1 millimeter. So let's apply it. I will save it. I need to write it down and build a FEA mesh. Okay, let's build it. All right. So again, meanwhile, the FEA mesh is meshing. I will start to setting up the TCFD simulation. So now, when the mesh is ready, we can enable the TCFD module, which will gives us a new item here, some new graphs for watching the instant residuals and final report. And let's start setting up the TCFD simulation. So there are again several menus. You can go from the up to the bottom like a wizard and set your simulation. So simulation type, first item to set, pretty easy. So you set the type of the turbo machinery design you are simulating. So here there is special type for hydro turbine, which each type includes specific treatment for the post-processing, for the HTML report. It uses specific efficiency formulas and so on. So therefore, there are so many simulation types for each basic design type from the turbo machinery world, let's say. Inside the physics, we start with the time management. Here you can set the steady state or transient simulation. So we will start with a simpler one, with a steady state simulation. How many speed lines? Speed lines are the simulation with different RPMs. So here we will running just the constant RPM. So we need just one speed line, and speed line points basically holds the different boundary conditions. So for hydro turbines, usually we are setting different flow rates to reveal the performance map. So let's start with three points on the speed line. How many iterations is needed? Usually you set more iteration than you expect, or from your experience. It differs from the complexity of the flow, sizing of the geometry, depends on the mesh size, and so on and so on. So I think for our case, 1000 iterations will be enough. The fluid properties are set here, so you can set some fluid defaults, or you can set your own parameters. So in my case, we can set, let's say, the dynamic viscosity is okay, reference density, I think in the original setup was 996, and reference pressure 1 atmosphere, I think will be okay. In multiphysics, you can enable the cavitation risk, which will give you some basic information about the possible cavitation. So it's just the post-processing. The cavitation risk takes the pressures, it computes the pressure of the saturated water pressure, and compare it. If the pressure is above, then it's okay. If it's below, it will somehow count into the statistics of the cavitation risk. And if it is enabled, you need to define the reference temperature. So let's say some real water temperature, I think this case was simulated with something like 2 degrees, which is, let's say, something, or 4 degrees, I guess. Yeah, 4 degrees. So which corresponds to these kelvins, or you can directly set, yeah, the temperature with the Celsius units. So this is important. These parameters, reference density, pressure, and temperature, is important for post-processing, as well as the gravity. So I always, for this type of simulation, the gravity should be off, which is somehow set by the zero gravity vector. But this magnitude of the gravitational acceleration is used for computing, for example, head from the pressure and other quantities. So this value is important. For the turbulence, we usually use k omega SST as a standard, but you can use, based on your experience, any other model which is available here. Rotating reference frame. So basically here you define the rotation speed. So if I visualize the CFD geometry again, and if I visualize, I think it's not here, but if I click the T mesh, we can see the axis of rotation. So it follows the plus Z direction. And to set properly the rotation, I like RPMs units, for example. So we can see that it should rotate in this way, and the direction of the rotation is defined by the right hand rule, let's say. So if your thumb points the axis, then your cross fingers, or then your other fingers points to the positive direction. So in this way, so this is the positive direction. So in this way, we need to set the negative value. And I think this turbine operates at 600 RPM. So we set it in this way. So it's important to check the sign, yeah, of the rotation speed. So it could be a common error when the simulation or this parameter is set. For the solver, here we can set number of processors. So my computer has 10. There is no limitations. Numerical order for water turbine, always use second. Runtime evaluated quantities. So here the averaging window is a parameter which makes an averaging, yeah, because the instant, let's say, instant results can oscillate even if we have a steady state solution. But from the numerical point of view, this usually for complex geometries and mainly for turbo machinery, you can always see some oscillation in the solution. So to get the robust solution at the end, it's clever to average these instant solutions. And this is the sizing. Usually the sizing should be something like 10 to 20% of the maximum iterations. So let's say keep it in the default 100 iteration as an averaging window. Write average quantities. It's a useful feature because in default the server saves only the last iteration. So it means when it's oscillating, it is, let's say, it saves some random unit within the oscillation at the end. But you would like to also see or visualize after the simulation also the average quantities from which the average efficiencies and average heads and so were evaluated. And also, for example, for FSI, you would like to use the average quantities, not the instant one, which tells you some random values, some random value within the oscillation, which the solution gives you. So always enable this. Efficiency probes. Here you define, let's say, the parameters of the main quantities to be evaluated, and basically the place from which they should be taken, because efficiency usually is computed from some rotating components from which the torque or power is evaluated, and also from heads or from total pressure differences. And so you need to set from which interfaces the total pressure difference, for example, should be evaluated. So the default should be take the inlet, take the outlet to evaluate these quantities like the pressure drop or something similar, and the torque patches to evaluate power and torque. So usually we should include all the rotating parts for the proper evaluation of the torque. And for example, so this will give you for example, the efficiency for the whole system, for the whole geometry, but you would like to also see the efficiency just for the impeller. Yeah, so you can set that the inflow will be inflow into this impeller part, torque patches, yeah, all the parts which are within the impeller, definitely, and the outlet will be the outlet from the impeller. And then you will see also the efficiency just for the impeller itself, just for the rotor. You can set or you can disable the flux weighted fields for efficiency. So all the boundary or the surface quantities are averaged, flux averaged, and if you disable it, it's a simple area average. So usually I think the default is the flux weighted values, or flux weighted averaging is standard. You can set the special forces evaluations. For example, if your STLs define each blade individually, then you can evaluate forces on each blade also individually by adding the force component, force probe here, and define for which part you would like to evaluate the forces or force coefficients. But I think it's not applicable here. In the probes, you can define an artificial point within your domain for watching, for example, instant values of pressure, velocity, relative velocities, temperature, if the solver gives you a temperature as well. So you can then get specific values for a specific point within your simulating domain. Well, the convergent check here, you set some checking criteria, and if all are satisfied within the simulation, then the simulation is stopped and ended before the maximum iterations are reached. Yeah, so it's pretty clever way. So let's say I will use just the efficiency probe based on the average efficiency. So I would like, so basically what this criteria says that, or this criterion says, is that if the averaged quantity, average efficiency oscillates less than 0.001% compared to the actual value, then the simulation is stopped. So basically here you define the tolerance, the relative tolerance, it's always relative to the actual instant value of this quantity. And if it's satisfied over the averaging window, then the simulation is stopped. The controls include some advanced parameters of the solver, so it's for advanced users, so they can adjust also the parameters of the solver itself. Maybe what is important to check is the minimum, maximum, and maximum pressure, which is used to, let's say, stabilize the solver, usually during the initial stage of the solver for the very first iterations. So keep in mind that if your application use some, let's say, high pressures or high velocities, then you should adjust them based on what you expect. Well, the boundary conditions, which basically defines your simulations. So here we set the inlet, outlet, and walls boundary conditions. For hydro turbine, I think for most application, we set the flow rate at the inlet and the pressure at the outlet. So we can set the volumetric flow rate, and here, because we have 3 points, we can set different flow rates at the inlet and at the outlet. I think the design point of this of this setup is something like 6.5 cubic meters per second. So I would like to compute 3 points around the best efficiency point. So let's say I would like to compute, let's say 7.5, 6.5, and 5.5 cubic meters per second. Usually it's better to start with the higher flow rates and going to the lower flow rates from the let's say solver convergence point of view, because it converges smoothly for higher flow rates than for the lower flow rates. Turbulent inlet quantities can be set here, so you can set the model quantities directly. So you can set the particle value of turbulent kinetic energy and specific dissipation rate based on your chosen turbulence model. So this is for K omega SST model, or you can, or you can use some help quantities to evaluate these parameters. So for example, the typical one could be to use turbulent intensity and hydraulic diameter. Turbulent energy intensity is intensity in percentage. So this corresponds to the 5% of turbulence intensity, which can be some typical value for internal flows. Hydraulic diameter is the diameter of the inlet typically. So in this case, when I go for CFD geometry and I go here for information, and here I check the inflow, then here we have the, let's say, the dimension. So we can say in Y and Z dimensions, which show us basically the diameter is 0.078. So this we can use it here. All right, where I am here. So 0.078 meters, and the reference velocity is some usual reference velocity for the best efficiency point, for example. So if my hydraulic diameter is this, then the surface could be also something 0.1, a little bit higher than 1. The surface area, so if I divide it here, so it's something like 6 meters per second. So this is, let's say, just a guess in which range the velocity is at the inlet. So 6 meters per second. That's all for the inlet boundary conditions. Now at the outlet, typically we use a fixed pressure with the 0. It's for the incompressible cases, it's always a relative pressure, and the absolute is computed based on, let's say, this value to which the reference pressure is added. So we are computing the case where the atmospheric pressure boundary condition is set at the outlet. Yeah, so always set 0, and then it's a standard for incompressible simulation to set 0 pressure at the outlet. It's not pressure in the pascals, but it's a relative kinematic pressure. Okay, for the walls, you can set a boundary type. So no slip is standard wall with friction, or you can set also slip, but it's not applicable here. But for some artificial walls, for example, you can set a slip wall boundary conditions, wall turbulence treatment, standard wall functions, let's say for rougher meshes. And if you have really fine mesh and with the inflation layer, which will give you Y plus closer to 1, you should enable this low Reynolds wall functions. But here our mesh is pretty rough at the moment without the boundary layer, so we'll definitely use the standard wall functions. Interface conditions. So now here how the method of communication between the neighboring components. So there are 2 approaches. First one is called here AMI, which is the arbitrary mesh interface, which corresponds to some kind of frozen simulation. So it's a point-to-point interpolations. So both patches will have the same values on both sides, and because in general the meshes are non-conformal, then some interpolation has to be applied. So this is done by this approach. Or for some rotational symmetrical cases where you can expect expect some symmetry in the circumferential direction, let's say. So you can enable the mixing plane approach. So mixing plane approach then average the solution over the strips, so kind of rings. For example, you can set 10 rings along the axial direction, and some averaging is done to communicate between those two parts. This is typical for axial machines when you can simulate just a periodic parts, so just one blade segment, and then you need usually to apply this mixing plane approach because there is no point-to-point correspondence, and one size or one side of the interface has a different shape from the other side of the interface. So basically, in this case, we can, let's say, apply both cases because in some way we can expect some symmetrical behavior caused by this symmetrical guide blades. But let's say we can keep this one, and then we can, for example, compare to the mixing plane approach the results. Initial conditions, we can set some let's say rough guess for the initial conditions. So usually just to set some meaningful values. Because the pressure at the outlet is 0, we can keep 0 at the outlet. Velocity, sometimes we can just help to only direct the flow based on the inlet direction, for example, or outlet. So if this is x, so I can set something like -1 or -2 meters per second, because 6 meters per second is at the inlet, let's say. This is also the outlet, it's very okay, and z direction, so flow goes, let's say, down, so we can set something like this, for example, but it doesn't matter. Usually it should start with 0 velocity as well. And initial turbine quantities, because we have already set them here at the inlet, so we can use inlet turbines values as initial, so then we don't need to care about the particle values here. And the last thing is the post-processing. Here you can adjust the report to your needs. So what are your favorite units? You can set them here. You can add some additional data files. So usually you can use some resulting file from the previous case, or some some data file with the measurements, and directly compare them with the current results, simulation results within the report, which is generated at the end of the simulation. You can also generate automatical visualizations, blade-to-blade views, and meridional average. So you can enable them by clicking these plus buttons here. Then you choose which mesh to be visualized. So for example, I would like to see the rotating component. If you properly set the types of the boundaries like hub and shroud, so it will automatically use them, or you can check them automatically. This must be set properly, because based on hub and shrouds, the, let's say, the modification or the transformation to some hexahedral shape to create the blade-to-blade views is done. So it needs the information about the hub and shroud. Then you can choose which fields to be visualized. For example, typical one, a nice one, is a relative velocity with a LIC filter, which shows you a streamline, some kind of streamlines pattern, and meridional average, again, for rotating component. And for example, I would like to see the static pressure. And the span here, what I haven't mentioned is let's say the relative coordinate between the hub and shroud. So this, let's say, cut will be done directly in the middle between the hub and shroud. The last two menus include the samples. You can, for example, sample for some additional post-processing any any surface and any field, or not any field, pressure or temperature. So usually this is for some additional FEA analysis in external tools, for example. And in miscellaneous part, you can enable writing the results into the CGNS format to be post-processed in another tool, something similar to ParaView or something like that. And right surface quantities, it's for, let's say, it writes down again the pressure and forces which can be mapped on an external tool for the FEA analysis, for example, if you want. Okay, so this was the TCFD simulation setup. I will save it. And the last thing is the FEA setup. So I will quickly go through the setup. So again, the new item after enabling FEA, the FEA module, and we will go through it pretty quickly, I guess. So here in the simulation, we set the physics or what we would like to simulate within the FEA analysis. So in this case, we don't need any thermal because we have no temperature here. We would like to map the forces from the CFD, safety results. So after enabling fluid structure interaction, we can see this menu. So we would like to map FSI or FSI, we would like to use FSI mapping based on the TCFD results. The patches will be which patches to take for the mapping. So basically the patches which defines our blade part. So we have the blade, hub, and shroud. Yeah, so we would like to map forces acting on the impeller. So map forces from pressure, definitely. Use relative pressure for computing forces. Yeah, it's the most safest way, because sometimes if your object is not floating in the fluid, then there can be one part of the pressure missing. Yeah, and if you enabling the relative pressure, then basically the pressures which the sides of the solid part which are not touching the fluid are treated that there is the atmospheric pressure or the reference pressure you have set in the TCFD. Use average quantities for FSI mapping. Yes, also I would like to use the average quantities, not the last iteration. Yeah, which can be somehow far from the average quantity based on the application, based on the simulation itself, of course. But I think this is the most common setup. You can also go for the model analysis. Yeah, so to get the frequencies. So for example, yeah, we can enable first 6 frequencies which FEA analysis will found. The solver, again, we can use as many processors we have. Basically, there are 2 solvers, direct and iterative. I think the choice number one is direct, which requires more, let's say, memory, but it is faster. But if you have lack of memory, you can go for iterative, which is, let's say, a little bit longer, but it doesn't need so many memory for the computation. You can choose finite element order first or second. So usually go for second, but if it doesn't work, try the first one. Use nonlinear equations. If the displacement, you expect the displacement of the for the displacement for the solid is larger than small, which is what is small and what is large, then you should go for the nonlinear equations, which is more complex model, but it takes more time. And if the displacement is really small, some kind of really small parts of millimeters, then you can go for this simple linear equation system. Yes, scripting. I don't want to bother with it with the scripting. Materials properties, you can set the material properties in a standard way. And last important thing is the zero displacement. So here you need to somehow fix You need to fix the solid, so where it is attached to some moving part. So you can use some artificial shape, or you can use the STL itself. So I can go, for example, for the hub rotor wall, I guess, which is, we can check it. So if I highlight the hub rotor wall, no, so this is not that one. So hub rotor wheel, yeah. So I would like to fix the solid within this STL. So hub rotor wheel. So I can choose the hub rotor wheel, and all the points within the solid mesh within the distance from this STL will be fixed. And I don't know the proper sizing, maybe 10 centimeters will be okay. All right, fixed quantities, usually it doesn't applicable here, but for example, if you have some simulation including the temperature, you can fix the temperature field at the given boundaries. And post-processing, you have two options for units. So I will keep stress units to megapascals and displacement unit to millimeters. All right, and when I am done, okay, check is okay. So I will just merge the mesh, because anytime you hit the right button, the mesh which is ready for CFD is rewritten on the disk, so it must be prepared again. All right, and I need to click the right button because I didn't do it, and meanwhile from the last write I have basically set up the whole simulation, so I need to write the new parameters on the disk. Now I can click the merge, or if you don't want to click step by step, you can click the run all, and it will run the whole workflow. But then in my situation, I don't want to recompute the mesh, so I will directly run the CFD simulation. Okay, and when everything is set properly, you can follow the instant residuals and other quantities live here. So if I click here, residuals, yeah, and now I can follow the residuals, but I can also follow other quantities. So if you create a new, let's say, new table or a new window, here you can choose the line chart view. And if you go to the FEA, TCFD, and you click here the quantities, so the quantities will be visualized here. And in the display part, you can choose any quantity you want. So for example, I would like to watch the efficiency, and the efficiency averaged. And you can manually zoom in the view part. So for example, for the left axis, which is this axis, I would like to see just the values between the 0 and 1. And you can watch then the efficiency live and all the other quantities. So you can do many items or many windows here and include all the other quantities which can be followed here in this table, like torque, power, head, and other quantities. And at the end of the simulation, when everything is ready, you can see the report here. You can switch between the steady state report, because we have defined we have two reports, and the FEA reports, and you can also follow them on the disk. So I will use my case, which is already computed. So I will go into the TCFD, and here the reports are stored within your case. So I will open the probe 1, which shows us the efficiency and all other quantities for the whole system. So this is an automatically generated HTML report. This simulation was set for 10 points. So here we see the head for 10 points different flow rates. Similarly for efficiency, so we have a nice efficiency curve. Here is some example how to compare it with the different data. So here the purple one is the current simulation and the blue one is some previous or measurement, or depends what user puts as an input for this comparison. Well, torque, axial forces, radial forces, and many other quantities can be watched and viewed here within the HTML report. The report is also interactive, so you can watch the velocity magnitude per interface. So you can choose the interface, graph tube outlet, and see the velocity magnitude there for each point and all the other quantities. At the end, you can see, for example, the blade-to-blade views, which are generated automatically. So you can see the streamlines on the blade-to-blade view, yeah, and similarly for, or in the same way for meridional average if it's set within the setting. So this is the TCFD setup and or TCFD simulation, and the FEA simulation has also its report. Here report, and we can open it. So it's the format is very similar. Some information about the solver, about the mesh, and some static analysis results like minimum maximum displacement, frequency analysis. So first three main frequencies for the model analysis, some displacement and other quantities relevant for the model analysis. And this basically we have for each simulated point, because we have 10 points, so 10 FEA analysis. The results can be anytime visualized. So if I open the already simulated case, so I can open it here. You can directly open the results from the manager. So let me just load the previous results, and you can anytime visualize the results for some manual post-processing. So you can use any features which PerView has together with our filters for the blade-to-blade view and meridional average. So I will hit the apply button, and for example, we can show the FEA analysis results. So if you go to the FEA run, and you can click here to show FEA results, so then the new item will appear here. You can get rid of all of this. So this is the FEA mesh, and on this mesh, if I go to the first point, for example, all right, so I'm not sure if I open it correctly. Let me do that again. Oh no, this is the mesh, sorry. So I think this file. All right. Okay, maybe I'm not sure if this simulation was finished for my, if I copied it correctly from my computer, but definitely in this way you can nicely visualize the results. Similarly for with the TCFD simulation, you can just hit this show CFD results and visualize, do any tricks here like slices, streamlines, clips, and so. So I think maybe this could be shown in some next webinars, just some custom visualization and so. So I think my my time is already up, so more than 1.5 hours of the webinar time. So what I have presented, how to quickly set the CFD simulation from scratch, from the input STLs, and basically within 1 hour we are able to set the whole simulation and play with it. So thank you, and I think it's time to go back to Lubos to conclude this webinar. Right, Lubos, are you there?
Yes, Radek, thank you very much for your contribution. It was great. I like it. And yeah, I think we can stay with your screen actually, and there will be a Q&A session, so we will answer a couple of questions, and then we will finish the webinar. Okay, so here are some questions, and you can also, everyone can ask questions, so feel free to ask your questions, and we will answer a few of them, and let's do that. Okay, so David is asking, what if I change the geometry input? Do I have to set everything again? Yeah, no, I can answer this. Of course not. It's as long as your geometry input, the STL files, have the same topology, you can replace them just in the directory and simulate again and again and again. So maybe we were not clear in this. You don't have, of course, you don't have to set everything from scratch all the time. So once you have set it, you save it, and you can run it on the same topology anytime you want. You can use multiple simulations or script and everything. So it's definitely ready for scaling the simulations in a big way. So these settings, like Radek did, you basically do it one time, just one time, and then you just reuse and reuse and reuse again and again the configuration file. Sure. Yeah. The next question. Armin Winkler, hi Armin, is asking, are the guide vanes fixed, or do they vary with the discharge? Sure, they're fixed. So the solver or the TCAE see them as fixed. So as you, basically they are represented in the input. So you load the STL with fixed position, and then you do the simulation. So then the typical workflow is you should have prepared a couple of a couple of variants of guide vanes, and just replace the geometry, or just one particular STL which represents another discharge or the guide opening. Yeah. So it's this, and well, the webinar is quite long, and so congratulations and thank you very much that you stayed with us so long. I think we should conclude. If there will be any question anytime later, feel free to contact us and we will answer it. I don't see any other relevant question, so we should conclude, I think. So I hope eventually you would see my screen. And Radek, please tell me when you see it.
So I think it's now in the switching phase.
Okay. Sometimes
so
it's
yeah, I will tell you when I
sometime. Okay, but anyway, we can talk. So the webinar is over. So we would like to thank you for coming. There will be maybe one last slide with the companies that already share our visions with us. So we will eventually show you if it comes up. And anyway, thank you for coming. And if you have any question or something, feel free to contact us. We will gladly answer all your questions. It's our job and also a pleasure. So feel free to ask. We'll do our best to make you happy. And we are looking forward to welcome you in our family, because we are a company who cares about our clients, and we hope we will collaborate in the future. So Radek, can you see my screen? Or?
Yeah, I can see the Q&A screen.
Okay, Q&A. Okay, anyway, yeah. So here's the what I promised. Here are a couple of brands. They're already our collaborators, and this is gonna be it. So Radek, do you have something to add?
Well, I think the webinar was long enough. So thank you for watching, and I hope we will stay in contact for future discussions and or cooperation. So thank you and see you next time.
Okay, thank you everyone. We leave you with that, and bye bye for now.
Bye bye.
Bye bye.